Okay, this is lecture 21, closed conduit flow. We kind of skipped a couple of numbers there in the lecture numbers. Don't worry about that. We may circle back, we may not. I guess it just depends on how the rest of the semester goes. Okay, so the objectives today are to determine energy loss due to friction for laminar flow and understand the Moody diagram. So the Moody diagram is going to be really important. And so really need to pay attention during that part, okay? So for evaluating energy loss for laminar or turbulent flow. So basically this is called closed conduit flow, but basically what we're looking at is flow in systems. And what's going to happen in these systems is we're going to start kind of dealing with the friction and the losses that occur. And so, as I said kind of early in the semester, one of the things that really excites me about this class is that we are going to deal with actually getting at friction and how to deal with it, okay? So in this case, in this class, with friction, we always refer to as head loss. And head loss is this guy HL, okay? And we're going to split it out into H sub F and H sub lowercase l. And then this is just kind of following the nomenclature of your textbook, okay? I mean, different books will do this different ways. And so the way that they are going to refer to this is that HF is the energy loss due to friction, okay, or resistance, okay? So this we can kind of think of as the flow is moving down a pipe, and there's just kind of this, you know, very low level but constant friction along the walls of those pipes, okay? And then this lowercase l here, H lowercase l, okay, this is going to be, you know, so-called minor losses. Okay, and these are going to be due to what we call viscous dissipation of turbulence. Okay, so this is really what's happening, you know, kind of like it's happening at fittings, at bends, at basically any kind of like thing that causes a disruption to the flow is going to create some turbulence or more turbulence, and then that's going to create more minor losses. So we'll talk about that on the next one, but for this lecture we're going to focus here. Okay, focus here on this lecture. Okay. It's interesting the way that your book and a lot of classes structure this, and I kind of agree with it, but this, the one we're going to do today, energy loss due to friction, is more difficult than the minor losses. And so I think that the reason, you know, a lot of times you'd like to layer things and the last thing to be the most difficult, but I think in this case it makes sense because we want you to get a little bit of practice dealing with this. Okay, so I'm going to kind of move down a little bit, and down here, okay, we're going to talk about this H sub F, okay? And I should note also that there should be in this formula up here an imaginary, it's not usually shown, but there should be a kind of an imaginary of basically summations here. Okay, because what we're going to do for the head loss between in your control volume between points 1 and 2 is we're going to add up all of the energy, the friction losses, and we're going to add up all the minor losses to get the total head loss. Okay, so it's never drawn that way, and we won't draw it that way here, but that is kind of how it should be thought. Okay, so what we're going to do here is we're going to think specifically about this friction loss. Okay, friction loss. Okay, and that of course is H sub F. And there's an equation for this, and this is called hold on, I'm going to give myself a little space here. So this is called the Darcy Weisbach equation, okay? And we're going to use this whether it's laminar or turbulent, okay? And then we're going to kind of split this out, and so it's going to be HF equals F L on D V squared on 2G. Now, as a brief aside, you know, so this is the Darcy-Weisbach equation, and I do want to note that this D right here, which we're using primarily because in this course we're only going to use circular pipes, but if you have a non-circular pipe, for a non-circular pipe. Okay, so you've got a rectangular conduit or something along those lines. This D actually is the what's called the hydraulic diameter, and it's going to be 4 times the flow area divided by what's called the wetted perimeter. Okay, so what that would mean, generally speaking, like let's imagine your conduit were rectangular, but if it weren't all the way full, then the area would be like this, and the wetted perimeter would be this portion on the outside that is wetted. Okay. We won't be using that in here. We're just going to use it as the diameter of the pipe. Okay, because that's because we're just going to use circular conduits in here. But in your coming courses, you might come across this. But that's just something to be aware of in general. Okay. For us, for circular, this is just going to be the diameter of the pipe. Okay, so. Okay, well, anyway, so getting back to this. So the key new term right here in all of this, and I don't really know, I mean, it's new, but so is this F right here. So this is the friction factor, okay? And that's kind of the key thing that we're going to deal with here. Everything else you should recognize, the V squared on 2G. This is the velocity head. The L, that's the length of the conduit or the length of the pipe in our case, and D is the diameter. Okay, so what we're going to do at this point is we're going to kind of split this out, and we're going to split this into the laminar case, which is kind of what we're working on today. So I'll kind of go over here and I'll do laminar, and then over here I'm going to do turbulent as kind of the counter case. Okay. And we're going to talk about how to get these in these different cases. Okay, and turbulent, I'm going to have to, I'm going to have to bring in some diagrams and things like that. But let's just kind of start with the laminar case. And the laminar case, I want you to recall a few kind of important things. Okay, so we've worked with this a little bit, but not infinitely. Okay, so Reynolds number. Okay. In this case is VD on nu. Okay, so this is the Reynolds equation for in a pipe. And in this case, it's less than 2,000 more or less, which tells you that this viscosity is relatively large. Okay. Now you might say, well, geez, it's only it's only 1/2000th of what's up top, or maybe more, but it's not, I mean, to call it large is one thing, but basically the key is that the viscosity matters. Okay, it's large enough to matter. Okay, and this is empirical, so they've just done enough studies and they realized that at this point, at that critical value, the viscosity plays a role. So the other things to remember is, so if we're talking about flow in a pipe, okay, so it's going to have a nice parabolic shape, okay, which indicates that V bar is V max over 2, which is why alpha equals 2.0. You're kind of like, okay, yeah, okay, whatever. We know all this. That's all review. But then the last thing is, and they've discovered this, again, empirically, so they just did a bunch of studies and they found this is what it is that F, that friction factor, is 64 over the Reynolds number. Okay, so this is a, key finding. And what's kind of interesting here is that F is not a function of the roughness of the pipe. Okay? So whether the pipe was 100% smooth or made of rough concrete or whatever, like, it has no effect on the friction factor. The only thing that matters is the viscosity of the fluid, the diameter, and the velocity of the fluid. So if we take this guy right here and we plug it in to our Darcy Weisbach equation, and it's really picking up my hand right now. So Darcy Weisbach is HF equals FL on D, V squared on 2G. Okay, we can plug this guy in. HF equals 64 over, in this case, I'm going to plug in the Reynolds number. And I'm going to leave that for 1 second. L on D, V squared on 2G. And let's go ahead and plug in this Reynolds number as rho v d on mu. And you're kind of looking at it going, wait, is that really what the... Well, what we're doing here is basically these two right here combine to give you nu, okay? Or 1 over nu, I guess. And so what we're doing here is we're just kind of lengthening this a little bit. I'm just trying to get to you kind of a standard form for this equation. So what it boils down to is if you plug all of that in, we end up with the friction factor in this case is 32 mu L V bar. Well, we should have had bars on all of these. V bar over gamma times d squared. Okay, so this is kind of the standard form for head loss or friction loss for laminar flow. Okay, so that's the one key. This is for laminar. Okay, and if you don't want to do it this way, you can always calculate the Reynolds number, and then you can calculate the Reynolds number on the side and then plug it into here and then get F and then plug that into Darcy Weisbach, or you can just do this. Okay, so this is kind of like a special Darcy Weisbach for the laminar case. Okay, so we're going to go ahead and use that real quick, and then we'll come back here. So let's zoom out. And let's go over here. We have a sample of how we might use this. Okay, so kerosene, specific gravity of 0.8 at a temperature of 68 degrees F, flows through a 10-foot long, okay, so 10 feet, we're kind of looking at like along here is about 10 feet long, 1/4-inch diameter pipe in a laminar flow regime. It's interesting that they would give us that it's laminar. We could calculate that, but it's given. Okay, find Q and V. Okay, obviously if you have Q, you have V, or vice versa, so that makes it kind of easy. I want to point out that before I really get into this, that there are the head losses in this system. There's a head loss associated with this entrance, and there's a head loss associated with this bend. Okay, those are minor losses, and we're going to ignore them for now. Okay, there's also this head loss due to friction along the walls. Okay, and that one we are not going to ignore. Okay, and that's kind of what we're dealing with in this problem. Okay, so I'm going to turn back to my trusty blue, and we're going to go ahead and solve this. And so in order to figure out this, I need to somehow get well, really I need to get at V. So, so we'll do P1 over gamma plus Z1 plus alpha V1 squared on 2G plus HP, which, you know, there is no pump, equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT, there's no turbine, plus the head loss. Okay, so let's get rid of the things that are easy to get rid of. Well, there's no pump in the whole picture. There's no turbine in the whole picture. So those are kind of the easy things. I guess the other thing that we should really be thinking about is, well, how do we where are our points, right? Almost even before we do pumps and turbines, we should do that. Well, the obvious points to me is to have point 2 right there at the opening and point 1 at the surface here. Okay, and the reason for that being that at point 1 and at point 2, both locations, we know that the pressure is atmospheric. Okay, so those go away. Okay, we know the elevations of both of these points. Let's do elevations in yellow. Okay, well, if I make this my datum, make that my datum. Okay, then I know Z1 is 1/2 foot. Okay, 0.5 feet. And I know, Z1 is 0.5 feet. And Z2 is going to be, wrong one. Well, it does not want me to erase that. Once is going to be 0. Come on, you can do it. 0. Okay. And then by the so-called tank or the Tahoe assumption, V1 is 0, so for the tank assumption, okay, or reservoir, whatever we want to call it. V2 we're going to need to get at by continuity, okay, maybe. or maybe we can solve it another way, I don't know, but that seems like a possibility. And then this head loss, okay, which thus far we've either ignored or they've kind of given us a formula for it. And we're going to split this thing apart into HF plus HL, okay? And for this problem, because we don't know how to deal with the HL, we're just going to cross that out. So just because it's going to make, well, because we don't know how to deal with it yet. Okay, so our equation at this point looks like this. So we've got 0.5 feet equals, yeesh. Okay, so we've got this alpha, which we're assuming, so we're assuming this is laminar, so I'm going to make this 2.0 V2 squared on 2G. I'm going to leave it like that for now. Plus, and then for this head loss, I'm going to insert the HF. And the equation for HF is F L on D V squared on 2G. Okay. So, so again, I'm going to pause right here, as I like to when I have the right time and place, to remember that this elevation is being converted into this velocity head, and some is being lost to friction. Okay, so that is what this equation is telling us. That is what this is all about. Okay, so let's see. So how do we do this? Okay, so 0.5 feet equals, let's write this as 2.0 times V bar 2 squared on 2 times 32.2, so that's 64.4 feet per second squared, plus, now I'm going to rewrite this as, let's just go ahead and rewrite it here underneath it as 32 mu, because this is laminar, L, V bar over gamma D squared. Okay, so we can plug all of those numbers in. So it's 32. The viscosity of kerosene at that temperature is 4 times 10 to the negative fifth pounds, seconds per foot squared, a miserable unit, okay, times 10 feet long pipe, times the velocity, which we're going to call this V2. Okay, it's really this, it's just the same velocity through the whole pipe, right? Okay, all divided by gamma. Now this is the gamma of the kerosene, so it's 0.8 times 62.4 PCF. Okay, and now we need the diameter of the pipe squared. So the diameter of the pipe is 1/4 inch, so we divide that by 12 and we get 1/48 of a foot squared. Okay, now, you know, if you're paying attention, and of course I wasn't, luckily I have notes, you'll notice that we've got something we've got a quadratic here. Oh wait, I screwed up. This is to the power 2, and this is to the power 1, because I accidentally put a squared right there. So let's just go ahead and erase that squared. Okay, so yeah, so if we solve this quadratic, which again, I'm not going to expect you to be able to do that on a test or anything like that, although you know, a lot of you have fancy calculators that could do that. But if we went ahead and solved that, we would get V2 equals 0.81 feet per second, which is pretty cool. And if we multiply that by the area of the pipe, we get Q equals 2.77 times 10 to the negative fourths CFS. Okay. So that's how we would do it. Yeah, so let's zoom out and let's zoom back in over here and let's consider the turbulent case. Okay, laminar turbulent. Okay, so in the turbulent regime, we will remember that, you know, this is, you know, kind of throwback, but the Reynolds number, okay, same formula. And it's going to be greater than about 4,000 in a pipe, okay? So in this regime, the viscosity is relatively large. Relatively small. Okay, and it could be the same flow or the same fluid. Viscosity is the same size, but it's relative to the velocity of the fluid or the diameter of the pipe. So viscosity is unimportant. Okay, and so that's kind of a key thing that we want to say. And so, keeping in line with kind of what we've done on the left, we'll kind of draw the velocity profile is very much, almost uniform. In fact, this was one of the true-false questions on the exam. Okay, so V bar equals V max. Oh, it's approximately, they're approximately equal to each other. Okay, so we won't even bother with the bar. They're basically equal, and that's why we say that alpha equals 1.05, which is approximately equal to 1. Okay, and so that's why we always do that. Okay, so in this case, HF, okay, the friction factor, F, is a function of the roughness. Okay, and so basically we're just going to use Darcy Weisbach on this side. There's no simple formula like we had over there. Okay, there's no simple formula. So in a second, we're going to I'm going to bring you to something that will kind of help us bring this all together. So let's, so what we'll do is we'll kind of zoom down here, and we have this diagram down here. This is the Nicarazi diagram. Okay, so that's, apparently that is not how we write. Okay, this is the Nicarazi. How do you spell Nicarazi? Nicarazi. Okay, and so what this guy did, Nicarazi, I assume it's a guy, I really have no earthly idea. Anyway, so he went out and he was trying to measure for this friction factor, as he calls it, or as it's called in your book, the resistance coefficient. This is your book's diagram, by the way, so you can find an exact copy in your textbook. But what you'll notice is that, so what he did is he basically just got a whole bunch of materials, a whole bunch of pipes of different diameter and different roughness. And so what he says, okay, I'm going to work with this thing KS, which has a name like the quote-unquote sand roughness height. Okay, and so what that means is that if you have a pipe or something, and you imagine the pipe's got little kind of like, bumps or whatever in it. So the size of those bumps, okay, that's KS. Okay, obviously they're not all exactly the same size, but there's kind of like a characteristic size to them. So that's what we call the sand roughness height. Okay, and so that's kind of the main thing. And then so he did is he divided that by the diameter of the pipe. So KS over the diameter, that's dimensionless because they both have units of length. Okay, and this is called the relative roughness. The relative roughness. Okay, and that makes sense. It's relative. It's how rough is it relative to how wide it is, right? So, you could think of it as kind of the percentage of the diameter that's taken up by these roughness elements. Okay, and so what he did is he had a whole bunch of pipes, and he used one pipe after another, and he just kept putting flow through it and measuring the flow rate. And from those, he was able to determine what this resistance coefficient was, okay, as a function of the Reynolds number of the pipe. And what's really interesting is that, well, there's a few things we want to talk about before we kind of get into this. First of all, this is a log-log plot. Log-log plot. Okay, so you'll notice that on this y-axis over here, okay, these things are not evenly spaced. Okay, luckily you're not going to have to read this particular plot because this will be very hard to figure out where, say, 0.55 is. It's kind of hard because it's clearly not right in the middle. And so, this one would be hard to read. But anyway, just be aware that this is logarithmic scale on the y-axis, is logarithmic scale on the x-axis as well. Okay, notice this is 1,000, this is 10,000, this is, this is 100,000. Okay, and And so 2000 is like somewhere maybe like right in here, maybe, I don't know, maybe in the 4000 about right here. I'm not exactly sure, but anyway, the numbers kind of get closer and closer as you go this way. Anyway, so what we're looking at here is that in the laminar flow regime, okay, notice that regardless of the roughness, okay, there was this like nice linear and log space relationship. And if you were to solve for that, you would get F equals 64 over the Reynolds number. Okay, notice it's in log space, so that's why it looks like a line here, even though clearly this is not the equation for a line in non-log space. Okay, and then and so you'll notice that here, okay, F is not a function of the roughness. Okay, that all of these fall on the same line. Okay, because it doesn't matter how rough the pipe is in that regime. Okay, now when we get to the so these are the low Reynolds numbers. Okay, so that's laminar. Over here we get turbulent. Okay, where it's turbulent, we have. Okay, so we'll notice where it's turbulent that the different roughnesses or the different relative roughnesses. Okay, now in this course for relative roughness we're going to use epsilon. Okay, but for the different relative roughnesses, notice that we get different lines. Okay, so like this right here is the most relatively rough pipe. Okay, and so it now splits out, based on the roughness. So over here, so over here F is not a function of roughness. Over here, F is a function of roughness. Okay, and so that's pretty critical. Okay, so the last thing to note is there is an area way over here, which they're kind of calling fully rough flow over here. Okay, and if you notice that over to this side, okay, the lines are relatively flat. Now, maybe I didn't exactly draw that right. Maybe it should be about like right there. Okay, but this is where we have what they call fully rough flow, or sometimes they'll call it wholly rough flow. And over here, F is only a function of roughness. Okay. Over here, on the laminar regime, F is only a function of the Reynolds number. F is only a function of the Reynolds number. Okay. In between, all in here, okay, this is transitional. Okay, and F is a function of Reynolds number and the roughness. Okay, so I'll put all this right here where hopefully it will make a little bit more sense. Okay, so if we go up here for laminar flow, F is a function of the Reynolds number. For turbulent flow, F is a function of the relative roughness. Okay, there is a transition region in here. Okay, transition, where F is a function of Reynolds number and the relative roughness. Okay, now keep in mind that most of this is in fact turbulent. Okay, most of that is in fact turbulent, most of that region. And this is just like what we call fully turbulent. Okay. And you're kind of like, well, how am I going to figure out if it's, and I'm going to show you that in a second. So don't get too worried about that. I'm going to show you how to deal with, when is it, basically we're going to get all of this off of one chart. So without further ado, let's go and get that chart. Let's go over here. So let's zoom out. Here we go. Here's this is the Moody diagram, and this is the one from your book, I believe. Okay. And so basically somebody, and it's a little bit blurry, I have no idea why. So I'm going to have to label some of this. I'm going to recommend that you get yours out and you look at it all. This is the relative roughness. So this is epsilon equals Ks on D. Okay. This right down here, this is the Reynolds number. Reynolds number equals VD on nu. And this is the friction factor, F. Okay, now typically, so what we've got here is we've got basically the Nicarazzi diagram, but this is the Moody diagram, and so this is going to cover basically every situation that you could possibly come across. And what's troubling about this, and what's hard for a lot of students, is that this is it's kind of a tough diagram. There's kind of a lot going on here. So let's start with the fact that it's log-log. So this is 10 to the third, this is 10 to the fourth, this is 10 to the fifth, 10 to the sixth, 10 to the seventh, 10 to the eighth. Okay, so you can see it's logarithmic. So notice this line right here. This is 1,000, 2,000, 4,000, 6,000, 8,000, 10,000, 20,000, 40,000, 60,000, 80,000, 100,000. Okay, and so that's how you read these. Okay, for the friction factors over here, again, it's logarithmic. So this is 0.008. This is 0.015, 0.03. I'm hoping that these are as easy to read as I can make them, or easier to read than what I'm having to do here. And then over here on the right, we've got, maybe I'll zoom all the way in, okay? We've got this relative roughness. Now the relative roughness, now this is really annoying, but they don't use scientific notation for relative roughnesses. I have no earthly idea why. I've never seen them use it. So like over here you've got 0, like this number is 0.1234.5. So 10 to the minus 5. Now why they don't write it that way, I don't know, but they never do it that way. Okay, so this is 0.00001. Okay, this is 0.00005. Okay, it's really annoying. That's just the way it is. It's just something you're going to have to be very, 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 very careful with. Okay, so the way we use this diagram, and that's really going to be the whole point of next class. So I guess this class is going to be relatively short because there's not really a whole lot to drive at here. Well, let's start with a few things. First of all, if you have a really low Reynolds number, so here's that 2,000. Let me get a nice yellow mark here. A yellow mark, perhaps. Okay, and so if you're at that in this below 2,000, let's not use yellow. Let's use green. Okay, so if you're in that 2,000 mark, let's see if I can get a ruler out here. So if we're in that 2,000 regime, then what we would do is we'd say, okay, let's just go right up here. Okay. Oh, look, we're in the laminar flow regime, which we already knew because our Reynolds number was 2,000, right? So if we knew our Reynolds number was 2,000, we already knew we're in the laminar regime. So we could either, in fact, the best way would be just to plug it into that formula, or we could follow this line up and then we could follow it over to the left, like that, and we would get a friction factor of about 0.034. Okay. My expectation, by the way, for you guys on this is that your friction factors should have 2 significant digits. Okay. F should have 2 significant figures. Okay. Sometimes you're gonna have to solve for these, so it's good to know, how far you have to go. So you should get the second significant figure right. Okay. Now, if you had something that was like, I don't know, maybe you were stuck at about let's say 4,000. Okay, so you're right here, 4,000. Okay, well now you're kind of really getting almost where you're out of luck. Okay, so remember there was kind of there's that region, right, 2,000 and 4,000. Okay, it's a transition region between laminar and turbulent. And if you're in here, if you're in this region, you're kind of guessing. Okay, you're kind of, there's just not really a lot of information. Okay, so it will almost never happen. Okay, more often than not, what's going to happen is you're going to have a pipe. I'm going to use red because it's going to show up on this. You're going to have a pipe and you're going to know a Reynolds number, or you're going to know, let's suppose you knew the Reynolds number and you knew the roughness. So let's just imagine that I knew that I had, so let's imagine I knew that, I had a pipe and the pipe was like the roughness was 0.03 inches and the diameter of the pipe was 10 inches, right? So I could say, okay, well then my epsilon is 0.003, Okay, so here we are right there, right? And I say, okay, well, what's my Reynolds number? Okay, well, let's just imagine that for whatever the problem may be, I just happen to know that the Reynolds number is 10 to the fourth. Okay, so it's 20,000 or it's 10,000. Okay, so I'm like, all right, cool. So now I have to get F. Okay, so if I'm doing this problem, or if I'm in the middle of a problem and I have to get F, so this is how you would read this equation, or this chart. Okay, so I would take this guy right here, okay, this 10 to the fourth, and I would draw the line up until I get to this line, okay, for 0.003. Now you'll note that right now we've got a nice one, okay, because it's falling exactly on a line. It's not always going to be so nice. You're going to have to do some guessing here, okay, and we go up until we hit right here. Okay, when we get right there, we draw a line to the left. Okay, so we're going to go like this. Okay, and so our F in that case is 0.061, maybe. Okay, so obviously in that case, if you got 0.062, I would take it. If you got 0.060, I'd take it. There's a little fudge factor in this, but you know, what you're going to find is that this number, whatever little errors you have in it, is not going to be the most important one. So let's do another one. Let's imagine another case. Let's suppose let's suppose we had a Reynolds number of I don't know. Let's suppose we got a Reynolds number. We solve for it. The Reynolds number is 20,000. Why is this popping up? Stop that. Okay, so let's suppose we had a Reynolds number equals 20,000. Okay, so that's 2 times 10 to the fourth. No, let's not do 20,000. Let's do 200,000. Okay, 2 times 10 to the fifth. Okay, so we're right here. 2 times 10 to the fifth. Okay, and let's suppose the pipe is smooth. So what that means for a smooth pipe is that means we need epsilon equals 0 over the diameter. So that's the equivalent of having an epsilon of 0. So let's suppose we have a smooth pipe. Okay, so basically I'm going to take this thing, and the smooth pipe is really the hardest situation. Okay, so we're going to move it up here like that. Okay, until we hit the smooth pipeline. So the smooth pipeline is right here. Okay, it's the bottommost line, to the best of my ability to draw it. Okay, once we hit the line, we're going to bounce to the left. Okay, and so this would be how you get your friction factor. Okay, and so that's, let's see here. So this is 0.0015, 16, 17, 18, 19, 20. Okay, so this could be, I would put this as 0.015. You could put 0.016, and that would be fine as well. Okay, so that's kind of how you get your friction factor. And that's kind of how you use this thing. Now, what I want to note before I leave this, and I'm going to talk about this next class, is notice that, so you see this dotted line. Maybe I'll use another color for this because it's really, really nice to notice this, is that this dotted line right here, okay, everything to the right of that, fully rough turbulent flow is what they're calling it, fully rough turbulent flow. And you'll notice that what's cool about over here is you notice these lines are all flat. Okay? So it's easier when they're flat. Okay? Because you don't have to think too much about it. Okay? You just have to kind of, you know, you can like if this was where our point was, it doesn't really matter what the Reynolds number is once you get above a certain value. Let me get blue. This is going to show up a little better. Okay, but once we get over to this side of this green line, hey, notice the Reynolds number doesn't matter for a very large, you know, it's like, in fact, nothing really matters. Okay, it's just as long as you know the roughness, okay, then this value is going to be easy to plot. Like you're always going to be, for that one, you get a value of about, I don't know, 0.024 or something. So if I were to trace that all the way over, 0.023 maybe. Okay, and so that's a really nice aspect, which we're gonna take advantage of next class. Okay, so this Moody diagram is in your textbook. I highly recommend you stare at it a little bit, and you know I'm gonna go over how to do this again next class. The last thing that I want to mention here. So there's two things I guess I want to mention before I completely shut this down is one, okay, what about this KS? Where do I get this KS? So a lot of times it'll be given. If it is not given, or if you're like working a homework problem or something along those lines, and it says like, a lot of times it'll just say like a concrete pipe or, you know, a glass pipe or PVC or whatever. And so what you'll do in those cases is you're going to go up here, or you're not going to go up here. You're actually going to have a textbook. But what you'll do, if it will allow me to scroll here, is in your textbook, there is this chart right here, which tells you what the KS is, okay? And so it'll say like, oh, it's glass. And you're like, oh, glass is smooth, cool. All right, so you know that it'll be that bottom line, okay? And so I want you to note one of the key things, this is in inches, this is in millimeters, okay? I don't know why they do this to you, but they do. Usually you're going to want to convert this into feet. Usually you're going to want to convert that into meters. Okay, because the key thing is that epsilon, okay, is KS over D. So whatever D is in, KS has to be in, okay, because they have to cancel each other out. This has to be unitless. Okay, so that's very, very, very important. You'll notice the most annoying ones that can show up are concrete and riveted steel because they kind of give you a range of values. My recommendation when you give a range of values is use one that makes it easy on yourself. So in this case, if I'm doing this and I've got concrete, well, I'm going to make this equal to 1.0 because that's the easiest number to work with. Okay? And, you know, your professor didn't tell you anything else, so use the one that you want to use. Or, you know, I guess I might use 3.0 if, for example, if the diameter of the pipe, if the diameter were like, I don't know, 3 meters, then I might be like, oh, well, my KS is going to be 3 millimeters, okay, because that's going to give me an epsilon of 3 divided by, or 3 times of 10 to the minus 3, which was like really easy to work with, right? So just pick one that works for yourself. Like in this case, I would pick one in the absence of any other knowledge, but otherwise I'm going to pick something that's going to make it easier for me to work with, okay? Same thing over here, okay? So if it gives you a range, just pick one you like. Okay, and I know that's going to make some of you very uncomfortable, but in like next class we're going to be iterating, and that's going to make some of you even more uncomfortable. Okay, so for starters, I know that, for example, this chart will make some people uncomfortable, and I can't really do a whole heck of a lot about that. But I will show you that we do actually have mathematical formulas that will replace this chart, but they don't really replace this chart, and that's the problem. So I'm going to show you what they are in a second. So if we zoom over here, I've got two equations up here, okay? And I want you to think about these as I bring them up here. So this first one, this is called the Colebrook equation, Colebrook, okay? And you can find these in your textbook, okay? And this is the exact solution of the Moody diagram for the entire non-laminar regime. Okay, so if you're staring at that, and if you're anything like I was as a student, I would immediately go, wait, we have an exact solution of the diagram? Why do we have the diagram if we have an equation? Well, in an ideal world, I would hope that you guys would look at this equation and hopefully you can see why we can't use this equation. Okay, I'm going to give you like a couple seconds to stare at it and see if you can see why it would be hard to solve for f using this equation. Really anything, but mostly f. Okay, and if you look right, you'll see that there's an f here and there's an f here. Okay, and so what that means is this is not an explicit equation. This is an implicit equation. Okay, meaning you can't just plug in and solve for it because you'd have to plug f on both sides. You can't get epsilon by itself. Okay, so there's no way to just solve this. So if you wanted to solve this, what you would have to do is you would have to estimate f, plug it in there, okay, solve for f here. Okay, once you had f here, you would use that as your second estimate of this f, plug it in, okay, solve for f a second time, second solve, okay, and what would happen is as you did this, you would get closer and closer until you had a solution. So you would have to iterate, okay? Now, the way that I solve these problems, when I solve these for, like, if I'm like, all right, I want to know what the exact solution is for your, you know, for an exam or something like that, is I use this equation and I use Excel, okay? And I use Excel because I can see it work. MATLAB would do better. I wouldn't have to watch it work, but whatever. Well, really, any Python or any coding language would be better. But MATLAB works just fine, and I'll show you how I do that. We're actually going to do this exact process, but we're going to do it using the Moody diagram, okay? And that's a standard thing that all engineers have to learn, and so you guys are going to have to learn. So that's the Colebrook equation. And next class we'll talk about how to iterate with Moody. You're probably not going to like it. I can't really do anything about that. Okay, so this equation right here, this is the Swamy-Jane equation, and I really argue with myself about whether or not I should show you this one. Okay, because the first thing we'll notice if we look at this is that it is explicit in F. F is on the left and it's not on the right. Okay, now the drawback, of course, is this incredibly complicated formula, but it's not exact. Okay, not exact. Okay, you are not going to be allowed to use this on a test. Okay, it gives you about a 3% error. Okay, but it's just something to kind of be aware of. I ultimately chose to just kind of go on the direction of trusting you guys. And so what's going to happen is some of you guys are going to have this question, which is like, well, okay, is 3% error too much? And I'm going to go ahead and say it depends. But we want to learn how to do this the exact way. We're going to have to learn how to do this using Moody. And so some of you are going to say, well, okay, if we're going to iterate, that means we're going to have a first guess of F. Okay, F, you're going to have to guess F. Okay, and we're going to go over how to do this next class. And so you're going, well, how am I going to know what to guess, right? Because it just seems like a lot. And I'm going to show you how. And so what some of you are going to ask, you're going to say, can I use this to guess? And the answer, of course, is yes, you may use this to guess. However, I'm going to show you how to guess better than that. Okay, so this is but this is too complicated. Okay, that equation is too difficult. Okay, because any guess you give is going to be faster than using this equation. Okay, so I'll show you how to do that next class. But right now, expect a really annoying iteration. I'll show you right now how we guess, by the way, just so that we can get ahead of the game a little bit. It works like this. You go, okay, well, I've got a Reynolds number I've got a roughness of 0.02. So this is my roughness right here. Okay, so this is the line that I'm going to be working on right here. Let me make this line really thick. That way I won't have to overdo it. Okay, so here we go. We're somewhere along here. Cruising along. All right, so that's what we're looking at. Okay, let's get a small little red line. All right, well now if I wanted to guess what the friction factor was along that line, and I don't know what the Reynolds number is yet, well, let's see. Almost the entire range of this thing, 3/4 of its range, has the same friction factor. So let's just use that as our first guess. And this will work most of the time. Okay, so that's 4.2, 4.4, maybe 4.5 or 4.6. So 0.046 maybe. And that would be how you would do your first guess. Okay, but I'm gonna demonstrate why we have to do that in next class. So anyway, hope you all are happy and healthy and doing well. And take care of yourselves and let me know if I can help with anything. Hope all's well. Bye.